Hey everyone, welcome back to the channel. In today's video, we are taking your calculus skills to the next level by exploring concavity and how it helps us in curve sketching. By the end of this lesson, you'll be able to use the second derivative to analyze the shape of a curve and sketch its graph like a pro. Let us get started and see how concavity reveals the story behind the function's behavior. Now, having any graph, let's say a point C, which is our inflection point, where the graph of a function has a tangent line and where the concavity changes, is what we call the point of inflection. So in this case, looking at this graph, right, it moves in this direction. Now when it gets over here, you could see that clearly it changes sign and moves upwards. So the point where it changes that sign is what we call the point of inflection. So in other words, point of inflection is where the concavity changes in a graph. So looking at this, you can see that clearly when you have something like this, that is where we call a concave down. So when you have this right here, we call this concave down. And when you have the opposite, when you have the opposite, which looks like this is what we call it concave up, and this is concave down. So we are going to use this idea to sketch any function that we are being given. Now quickly, let us go ahead to solve some questions involving concavity. So the first question has got to do with, we are to determine the concavity and find the point of inflection of the function s cubed minus 3s squared plus 2. One thing that you have to notice, the point of inflection has got to do with the second derivative. So first of all, we have to differentiate our function. So we have f prime of x. And remember, if we differentiate the function, if we differentiate s cubed, we have 3s squared. If we differentiate negative 3s squared, we're going to have negative 6x. And if we differentiate the constant, it goes to 0. For the second derivative, we have to differentiate once again. So we have 6x minus x. So concavity is where the second derivative fails to exist, or it is equal to 0 over here. So in this case, there is no x value that will make this function undefined. So what we have to do is to set f double prime to be equal to 0. So this implies that 6x minus 6 is equal to 0, which implies that 6x is equal to 6, which implies that our x is equal to 1. So our inflection point, we have x equal to 1. So to find the corresponding y value, you have to substitute your x into this. So let's find f of 1. We are going to have 1 cubed minus 3 1 squared plus 2. And this is 1 minus 3 plus 2, which is equal to 0. So our inflection point of the function is our x corresponds to 1 and the y coordinate is 0. So we have our inflection point to be 1, 0. Now we have to determine the concavity. In determining the concavity, what you have to do is to draw your number line. So just as we did previously, so we draw a number line. We have an inflection point x equal to 1. We have infinity here, we have negative infinity here. We can pick a number between this and this. So we can say 0. So in that case, we remember to find the concavity, you evaluate at the second derivative. So our second derivative was 6x minus 6. So in this case, we have 6 times 0 minus 6, and this is negative 6. So it means that this is going down. And now between this interval, we can pick 2. So we have f double prime of 2, and this is 6 times 2 minus 6, and this is 12 minus 6, which is positive 6. So it means this goes up. So you can conclude that the function is concave up on 1 to infinity and concave down on negative infinity to 1. I hope this is clear. So the only difference between this and finding where the function is increasing and decreasing is for concavity, it has got to do with the second derivative, and we also deal with inflection point. But checking to see where the function is increasing and decreasing, remember, we deal with the first derivative and the critical point. So that's the basic difference between them. Let's look at a different example. We have f of x to be equal to x to the 4th over 4 minus 2x squared plus 2. So we do the same thing where we find our f prime of x, and in this case, remember 1 over 4 is a constant, so we can bring it outside. And if we differentiate s to the 4th, we have 4s cubed. Then if we differentiate negative 2x squared, you have negative 4x. Again, 2 is a constant, so it goes to 0. So we just have to equate this to, we just have to equate this to 0. And if we do that, remember, this 4 can cancel this 4. So we just have s cubed minus 4x left. So this is x s squared minus 4 equal to 0. Oh wait, let's see if everything is right over here. So we have, so this was the first derivative. Remember, we have to find the second derivative. So the first derivative is s cubed minus 4x. So the second derivative will be 3s squared minus 4, and this is when we equate to 0. So f double prime of x equal to 0 basically means 3s squared minus 4 equal to 0. There is no common term, so we can send this 4 to the right hand side, and that becomes positive. So if we divide both sides by 3, we have 4 out of 3. So our x will be the square root of 4 out of 3, which is equal to plus or minus the square root of root 3. So remember, the square root of 4 gives 2. Square root of 3 is a radical, so we just leave it as it is. And since it is a square root, we have plus or minus. So we have 2 inflection points. So we have x to be equal to negative 2 out of root 3, and x to be equal to positive 2 out of root 3. So let's see where the function is concave up and concave down. So we have negative infinity here, negative 2 over root 3, 2 out of root 3, and infinity. So first of all, let's pick a number that is between this. So we can pick, let's say negative 2, and we evaluate using this right here. So we have 3 times negative 2 squared minus 4, and this is 3 times negative 2 squared is positive 4 minus 4, and this is equal to 8, so this goes up. Now we move to, let's say, f double prime of 2. So f double prime of 2 is basically 2 or 4 somewhere here. So we have to do the same thing, 3 times 2 squared minus 4, and that will also give the same result. So it means this also goes up. Now the last one, we can pick a number between this and this over here, so we can select 0. So we have f double prime of 0, and that is 3 0 squared minus 4, and this is minus 4. So basically this over here goes down. So then we can, to find the inflection points, remember you have to find the x and y coordinates, right? So we have to substitute this back into our function to find the corresponding y value. So let's find the first one. For the first one, we have to find negative 2 over root 3. So that is basically negative 2 out of root 3 to the exponent of 4 minus 2, then negative 2 out of root 3, then squared plus 2. So this will give you, if you do that, this is negative 2 to the exponent of 4 is positive 16, then root 3 to the exponent of 4 is 9. Negative 2 to the exponent of 2 is positive 4. Root 3 to the exponent of 2 is just 3 plus 2. So this is 16 out of 9 minus 8 out of 3 plus 2. So this will just simplify to 10 out of 9. Then you do the same thing for 2 root 3. So that is 2 over root 3 to the exponent of 4 minus 2. 2 over root 3 squared plus 2. And if you do the math, it also ends at 10 out of 9. So we have our inflection point. We have negative 2 out of root 3, 10 out of 9, and then positive 2 over root 3, 10 out of 9. Now, we can see that it is concave up on. So looking at this, it's concave up here and here. So from negative infinity to negative 2 over root 3, and then from 2 over root 3 to infinity. Then it's concave down on negative 2 out of root 3 and 2 out of root 3. Yeah, so I hope this explains it enough. Let's look at another question. So for the third question, we have to sketch. Now we have to sketch. So sketch the graph of the function x to the power of 4 minus 4x cubed plus 10. So to sketch this graph, there are some things that you have to do first. So first of all, let us find the local extrema. Okay, so to find the local extrema, remember, first of all, you have to find f prime of x. So if we differentiate our function, we are going to have 4x cubed minus 12x squared. Then we set this to equal to 0. So this implies that we have 4x cubed minus 12x squared equal to 0. So over here, we can factorize 4x squared out. And if we do that, we have x minus 3 equal to 0. So this basically means we have 4x squared equal to 0 and x minus 3 equal to 0. So this equal to 0 and that one equal to 0. Over here, if we divide both sides by 4, you still have x squared equal to 0, which is basically s is equal to 0. And this is s is equal to 3. So we have two critical points. So we can draw our number line here. We can have this. We have negative infinity, we have 0, we have 3, and we have infinity. So we have f prime. If we pick a number here, we can pick negative 1. And we are testing using this. So we have 4 negative 1 cubed minus 12 negative 1 squared. And if we do that, you have negative 4 minus 12, which is negative, so it goes down. And also we can pick a number here, so we can pick 1. If we do that, we have 4 times 1 cubed minus 12 times 1 squared, and that is 4 minus 12, so this also goes down. Okay, so in this range, we can select 4. So f prime of 4 is 4 times 4 cubed minus 12 times 4 squared. And that is 4. 4 cubed is 64. 4 squared is 16. So yeah, pretty much that is positive. So that goes up. So we can use the first derivative test, right? So using the first derivative test, we can see that there is no extremum. Remember, if the signs are the same, if they are going in both directions, right, since they are going in the same direction, then we can see that there is no extremum at x equal to 0. So at this point, there is no extremum. Now let's check this. Do you have a local minimum or a local maximum? So at x equal to 3, we have a local. Over here, since it goes down before it goes up, we have a local minimum. Okay. So let's see. Now, since we have critical points 0 and 3, let's find their corresponding y values. So f of 0 will be 0 to the 4th minus 4, 0 to the cubed plus 10. So that will give you just 10. And f of 3 will give you 3 to the 4th minus 4, 3 to the 3rd plus 10. And that is 3 to the 4 is 81 minus 4. 3 to the 3rd is 27 plus 10. And if we do that, we are going to end up, let's see, so this is plus 10. So that is just negative 17. So our critical points are 0, we have 10. So we have 0, 10. And for 3, we had negative 17. So we have 3 and minus 17. Okay. Also, we can also have one set of information over here. We can see where the function is increasing. So it's increasing on 3 and infinity, and it's decreasing from negative infinity to 0, then from 0 to 3. Okay, so now since we've gotten to know the local extremum, we've gotten to see where the function is increasing and where it is decreasing. Let's check where the function is concave up and concave down. So from the previous slide, we got to see that f prime of x is 4x cubed minus 12x squared. Yeah. So now to find concavity, we have to check for the second derivative. So if we differentiate this once more, we have 12x squared minus 24x. Then we set this to 0. So we can factorize this out. So we have x minus 2 equal to 0. So this means 12x is equal to 0 and x minus 2 equal to 0. So we have x equal to 0 here and x is equal to 2. So we have two inflection points, but we have to find the corresponding y values, right? So already we know that f of 0 gives 10. So let's find f of 2. F of 2, remember we are putting it back inside this. So f of 2 is 2 to the exponent of 4 minus 4 2 cubed plus 10. So this is 16 minus 4 times 8 plus 10. This is 16 minus 32 plus 10. So that will give you just negative 6. So we have inflection point. We have 0, 10 and 2, minus 6. So now let's check where it is concave up and concave down. So we can have a normal line here. So we have negative infinity, we have 0. Let me space it out a bit. We have 2 and we have infinity. So right here, we can have negative 1, right? So we have f double prime of negative 1, that is 12. So now we are using this. So we have 12 negative 1 squared minus 24 negative 1. So that is just 12 plus 24. So that's positive, so this goes up. And here we can select 1. So we have f double prime of 1. So 12 1 squared minus 24 1. That is 12 minus 24. So this is negative. Okay. Now let's check f double prime of 3. That is 12 3 squared minus 24 times 3. So that's just 12 by 9. 24 times 3 is 72. 12 by 9 is 84. So that is a positive number, so this goes up. And one thing to notice, to check to see if these are indeed inflection points, the signs has to alternate. So clearly you see that at 0, we go from up to down, meaning the signs also alternate, so it is indeed an inflection point. At 2, we see that the sign also alternates, we go from down to up, so it's also indeed an inflection point. So that's one thing to note as well. Okay, so now we can conclude to say that the function is concave up on negative infinity to 0, and if we draw the graph, this should depict it as well. And from 2 to infinity, and it is concave down. It's concave down over here, 0 to 2. So now the next thing to do is we have to sketch the general shape of the graph. In sketching the general shape of the graph, we are going to need these two number lines. Let me have this here. And we're also going to need this. Okay, so this will show us how to sketch the graph. Let me clean this. So in sketching the graph, remember this is where we got to see it's increasing or decreasing, and this is concave up and concave down. Okay, so now one key thing, there's a trick, right? So looking at the endpoint, you have negative infinity, 0, 3, infinity, then 0 and 2. We want to combine all these points. So let's write them once more. We have negative infinity, we have 0, but before we go to 0, remember we have 2 here. So we can write it 2, we have 3, then we have infinity. We don't have any terms left. So now we can combine these two. So we have from negative infinity to 0, now this and this. So we have 0 and 2, this and this. So we have 2, 3, and the last set will be 3 and infinity. So we want to see from negative infinity to 0, is the function increasing or decreasing? Now we got to see that negative infinity to 0, the function was decreasing. From 0 to 2, is it increasing or decreasing? 0 to 2, 2 is somewhere here. So clearly, at 0 to 2, the function is also decreasing. From 2 to 3, now 2 to 3 is 2 is somewhere here. So 2 to 3 means the function is decreasing again. And from 3 to infinity, that's where we've got to see that the function starts to increase. So it increases here. So we are trying to combine everything. Okay. Now, let's check for concavity. For concavity, from negative infinity to 0, we got to see that it was concave up. Right here, we got to see that it was concave up. From 0 to 2, we got to see that it was concave down. From 2 to 3, remember 2 to 3 is within this range. So we got to see that this was concave up, and 3 to infinity is also in that range, so this is also concave up. So one thing that you have to note is okay. Remember, if it's going this direction, then this is concave down. If it's going this direction, this is concave up. Okay, so we are going to use this set of information right here to see the shape of our graph, right? Okay. So from negative infinity to 0, we got to see that the function was concave up. So concave up, we use this graph. Okay. Now for concave up, it shows that it's going down. So going down, we use this direction right here, as I've indicated. So it's going to look something like this. from 0 to 2, we're going to say it's concave down. So concave down, we have to use this map. And it's also going down. So if it is going down, which one do we choose? So, okay, so I made a mistake over here. So with this, it should have been something like this. Okay, so from 0 to concave down, we use this. That's fine. And it's going down. So if it's going down, we use this direction right here. So for 0 to, it's concave down. So it goes, we are going to use this. Okay. And the function is also decreasing. So meaning it's going down, this arrow. So it's going to look something like this. Okay. Now for 2, 3, it is concave up. So we have to use this right here. And it is going down. So since it is going down, we have to use this direction. Now for the last one, 3 to infinity, we see that it's concave up, so we have to use this. And now the function is also increasing, so we have to use the right hand side. So it goes something like this. So this is the general shape of the graph. So we are going to use these to help us in drawing our final graph. Okay. So now let's draw our graph. Okay, so we have, let's say 0, 1, 2, 3, 4, and 5. Let's say we have 5, 10, 15. This is not drawn to scale. So -5, -10, -15, -20, -1, -2, -3, -4, and -5. So now we are going to use all the points that we had. So first of all, let us plot our critical point. So for critical point, we had 0, 10. So 0, 10, 0, 10 will be somewhere here. So this is 0, 10. We also had 3 and -17. So if 3 is here, -17 will be pretty much somewhere here. Okay, so now let's plot our which again the local minima and the maxima. We got to see that our local maxima over here is equal to 3 was a local minima, and 3 corresponds to -17. So we've already plotted that, so it's fine. Let's look at our inflection point. We have 0, 10 over here, which we've already plotted. We also have 2 and -6. So we have 2 here, -6 will be somewhere here. 2 and -6. Okay, so I think these are the points that we need. So now, let's go back to the shape of our graph. We said from -infinity to 0, it looks this way. So from -infinity, so we are going to use these 3 points that we plotted to help us. From -infinity to 0, basically, we are moving from this direction to this. You see how this how it looks. So we have something like this here. And now from 0 to 2, it goes down. So 0, this is 0 to 2. So it goes down like this. Okay. Then from 2 to 3, it kind of bends. So from 2 to 3, so this is 3 and this is 2. You see it bends like that. Okay. Then from 3 into infinity, it goes up again. So in this case, from 3 to infinity, we are going to see it going up like that. So we have something like this. So this is the shape of our graph. So now let's look at what we had. Over here, we said that the function is concave up on negative infinity and 0. So let's see. This is negative infinity and 0. You see, clearly it's a U sign, so meaning it's concave up. And it was also concave up on 2 to infinity. Clearly you see that from here is 2, right? From 2 to infinity, we also see a U sign. So this means our graph is correct. Also, it was concave down on 0 to 2. This is 0, this is 2. Clearly over here, you can see that it bends down. So that is also correct. Now let's check for our inflection point. So we got to see that our inflection points were 0 and 2. 0 and 2 were our inflection points. So let's see. So clearly at 0, you can tell, you see at 0 the function changes sign, right? At 0, here is 0, it goes down like this. Okay. And at let's see, it was 0 and 2, and also at 2, it also changes sign right over here. You see it's bent like that. So there is an inflection point indeed. And also, what else, which information do we need? Again, I think that is all. And yeah, the function was decreasing from negative infinity to 0 and 0 to 3. So from negative infinity to 0, yes, it was, you see it was going down, so it was decreasing. And 0 to 3, this is 0 to 3, 0 is here, 3 is here. Clearly we see that it was going down again. That's true. And we got to see that the function was increasing from 3 to infinity, and as we saw, it was increasing. Yeah, so that brings us to the end of the video. So that is wraps on our discussion on concavity and curve sketching. With the tools we covered today, you are well equipped to analyze functions and draw accurate graphs. If you enjoyed this video or learned something new, please like, share, and subscribe for more calculus content. And as always, feel free to leave your questions or suggestions in the comments. Thanks for watching, keep practicing, stay curious, and I'll catch you in the next video. Bye.